Hello, and welcome to Lesson 4 of this Introduction to Probability of Wolfram. This lesson is about axioms of probability. Let's begin. What's an axiom? It's a proposition seen as self-evident, such as the sun always rises to the east, something that everybody can agree on. To prove something, you need to assume something else. Axioms of probability serve as a basis of probability, but also as a justification of probability theory. From these axioms, all probability theorems can be proven. Notice this is a mere justification. Axioms are not the historical origin of most theorems. As you saw in Lesson 1, probability theory is quite old, but these axioms were only invented in 1933 by the Soviet mathematician Andrei Kolmogorov. Indeed, most of the discoveries explained in this course were discovered because they simply worked, and mathematicians had to explain why. So, why start with axioms of probability in this course? Well, these axioms define the most fundamental concept in this course, probability. How does one define probability? We could equivalently say, how does one quantify how possible an event is? If I were to take a poll among the students of this class, the popular answer would likely be frequency. Let's say on M experiments, an experiment E occurs k times. Then you could use the frequency to define the probability by creating the following axiom. The probability of the event is k divided by m. You would get a fractional number. We could then make m tend toward infinity, since we tend to assume that empirical measures tend to theoretical measures. But we run into a problem. If k divided by m defines a probability quantity, then it intuitively should be some kind of a consistent or constant number, which is problematic. An axiom needs to be self-evident, and the fact that k divided by m converges to constant is far from self-evident. So Kolmogorov uses more self-evident axioms as the basis of probability. It's a three-step program: one axiom for events, one for the sample space, and one for the relationship between events and the sample space. To quantify how probable a particular event is, first quantify the probability of an impossible event. This is intuitively nothing, a null element. By convention, in mathematics, null quantities are denoted by 0. So use 0 to represent the probability of an impossible event. To describe an event that always happens, choose 1. From this, we get all fractional probabilities, like 1 divided by 2 or 1 divided by 6. But why 1? Well, it makes the calculus simpler. It's not the only probability standard, however. The percent notation chooses 100 instead of 1. In fact, percent comes from the Latin percentum, meaning per 100. So we could call our choice of 1 to be a per 1 notation. Intuitively, the probability of any event E is somewhere between never and always. So that would mean any event has a probability between 0 and 1. Then what is the probability measure for sample spaces? Well, the sample space is the set of all possible outcomes. It encompasses all probabilities. Since the sample space defines all that is possible, the event that the result is part of the sample space will always happen. Thus, we define the probability of the sample space as 1. Now, both events and sample spaces are quantified. How do you relate one to the other? For that, we need mutually exclusive events, where every event shares no outcome with any other event. In other words, every pairwise intersection is null. The concept of size from set theory is well established, so let's use one of its mechanics. The size of A union B is the size of A plus the size of B minus their intersection. The intersection is removed since it's null, and so it implies in this context that union becomes equivalent to addition. To achieve the same behavior in probabilities, set the probability of the union of mutually exclusive events to be equal to the sum of each event probability. Broadly speaking, all this allows us to add probabilities to get even larger events. If the events add up to 1, then their union is the sample space, which solves the problem. You now have a way of relating the sample space to a collection of events. So let's say you roll a 6-sided die. What's the probability that you get an even number? Each face is equally likely and mutually exclusive, since a die can only indicate one number at the same time. So if P is the probability of getting a 1 and there is 6 mutually exclusive events that form the sample space, then solving the equation where the sample space probability is 1 results in P equal to 1 over 6. Using axiom 3, adding the probability of 3 mutually exclusive events, you get 1/2. We just explained what union and intersection of sets means to probability, but what about the complement? Well, from axiom 2, we know 1 minus the probability of an event should be the probability of the exclusive rest of the sample space. In other words, its complement. So if there's a 30% chance of rain tomorrow, then there is a 70% chance that it won't rain. At this point, we can prove set theory formulas from probability theory. The next proof might be difficult for those that are not experienced in set theory. The goal here is just to show how set size and event probability are similar. Consider the events A and B as well as their sample space S. Then A union B is the same thing as A union A complement intersection B, which gives us this formula since A and A complement are mutually exclusive. With a bit of isolation, we get this. Now B is the same thing as the sample space intersection B. The sample space is the same thing as A union A complement. So distributing, we get this. Now the probability of B, we still plug the same thing, and because A and A complement are mutually exclusive, we get this, and with a bit of isolation, we get this. Now we can compare the probability of A complement intersection B on both sides, and we get this formula, and with a bit of isolation, we get the probability of A union B is the same thing as the probability of A plus the probability of B minus the probability of their intersection, which is the same formula as we saw for size. Suppose you and your friend did not study for the exam you just completed. There's a probability of 0.4 that you passed, 0.6 that your friend passed, and 0.3 that you both passed. What's the probability that at least one of you passed? Well, the probability of A plus B minus the probability of their intersection, so we get 0.7. Since the probability of A union B is the probability of A plus the probability of B minus something that is non-negative, then the probability of A union B is less than or equal to the probability of A plus the probability of B. We can then create a similar formula as axiom 3, but less precise due to the inequality. This is Boole's inequality. It means that for general events, the probability of union is less than or equal to the sum of each event probability. For example, to get to work, you could use the car, the train, or the bicycle. However, tomorrow there is a 0.05 probability that your car will not start, a 0.02 probability that the train station will be closed, and a 0.35 probability that it rains, and so you cannot use your bicycle. So what's the highest probability that any of those events happen? We can just add the different probabilities and we get the union, the maximum possible union. So in short, probability is based on 3 axioms. Probability is bounded by 0 and 1, the sample space has a size 1, and for mutually exclusive events, you can transform union into addition. From these axioms, useful formulas can be derived using set theory, notably the complement, the probability of union, and Boole's inequality. The next lesson extends these concepts by using common assumptions practically.